Hello and welcome to this video for Chemistry 30 Thermochemistry lesson number 3. Today we're going to look at how to calculate enthalpy changes. So in the last video we did an introduction into enthalpy changes and talked about what enthalpy meant as well as different ways of communicating it. Now we're going to learn one of the formulas for calculating enthalpy. So remember enthalpy, another word for enthalpy is energy or heat. And in a formula, we're going to write it as delta H. Remember, it can also have a little letter written, R meaning reaction. The heat of this reaction is, okay? It could be specific with a C for a combustion reaction and so on. But generally speaking, in order to find the enthalpy change of a reaction, you're going to take the number of moles and multiply by, remember what we mentioned in the last video, something called molar enthalpy, okay? So the delta H again is the overall energy of a reaction. And it's usually measured in kilojoules. Whereas the H by itself, and it still has that little R that goes with it, again just meaning for this reaction, what is the molar enthalpy referring to the molar enthalpy of, okay? So molar enthalpy is measured in kilojoules per mole, most commonly. Now, in order to find delta H, you obviously have to be given delta H, or sorry, if you're trying to solve for delta H, you have to be given H, as well as the number of moles. N is the number of moles. Now, there's a few ways that we can calculate the number of moles. Remember back in Chem 20, we learned how to calculate moles using the formula mass over molar mass. Now you could also use the formula concentration times volume. But there's a third way that you can find moles, and that is the balancing coefficients. When you have a reaction written out, like we talked about in the last video, when we had sulfur dioxide reacting with oxygen to produce sulfur trioxide. These balancing coefficients of 2's means you have 2 moles. So I have 2 moles of sulfur dioxide reacting with an invisible 1 mole of oxygen to produce 2 moles of sulfur trioxide. Those are the mole values, okay? Now your delta H and your H, remember, need symbols whether they're endo or exothermic. The H and the delta H always have the same symbols for the same reaction. If the reaction is endothermic, they're both positive. If the reaction is exothermic, they're both negative. Now, sometimes the question will give you the symbol, but sometimes you have to put it there yourself. Again, if it's talking about energy being released or energy being produced or energy being lost, that means it's exothermic. If it says energy is being absorbed or gained or reacting with, then that means it's endothermic and you need to put a positive, okay? Now, we'll look at how to use this formula in a couple of examples. So I'm given the following reaction. It is showing me the combustion of ethane, and it's given to me in delta H notation, where the delta H is written off to the side as its own value. Notice how it's negative, representing an exothermic reaction. Notice how it also has a little C here, because this is specific to a combustion reaction. Now, the reason the equation is given and the delta H is given is because they go together, okay? This delta H is the amount of energy released when 2 moles of ethane reacts with 7 moles of oxygen to produce 4 moles of carbon dioxide and 6 moles of water. For this balanced equation, this is exactly how much energy is released, okay? So we are given the delta H here, and it is asking us to calculate the molar enthalpy of combustion, again, because this is a combustion reaction, for oxygen. That's the key here. You could find the molar enthalpy of any of these substances, okay? For the ethane, the carbon dioxide, the water, and the oxygen. In order to solve for it, if I have my formula, delta H equals NH, and again, if you don't put the C's for this combustion reaction, it's not a big deal. If it's easier to look at it as delta H equals NH, that's fine, okay? The C's again are just there because it is specific to this combustion reaction. So if I want to solve, actually let's remove the C's just to make it a little easier. Okay, a little more straightforward. So if I want to solve for my H, I need to rearrange the formula by dividing both sides by n. So I'm left with the formula H equals delta H divided by n. Okay? I'm going to put the C's back because it's bugging me not to have the C's there. Just kind of a notation thing. So my delta H was negative 2856.8 kilojoules, but what is my N? So there's no mass given, there's no concentration and volume given, but we have a balanced chemical equation that shows when 7 moles of oxygen react, this much energy overall is released. So if we want to figure out what that is per mole of oxygen, we're going to divide by 7 moles of oxygen. Okay, that's the balancing coefficient in front of the oxygen. Now for sig digs, the 7 is a counted number, so it's not included in our sig digs for figuring out how many we should have, right? The number 7 has 1 digit in it. That doesn't affect our answer. We go back and use the actual values that were given, which is the delta CH, and that's how many sig digs we can have. So if you put this in your calculator, negative 2856.8, and divide by 7, you're going to get an answer, again negative. If the enthalpy change is negative, the molar enthalpy also has to be negative. This is an exothermic reaction. For every substance, it's an exothermic reaction, so it's always negative. They're always the same for a reaction. 1, 1, 4, so on, and notice how my units are kilojoules per mole because I'm getting a molar enthalpy. So for sig digs, it looks like we're going to need to have 5 sig digs. So we're going to cut it off right there. The 4 again is not big to round anything up. So my molar enthalpy of combustion for oxygen is negative 408.11 kilojoules per mole. That is your final answer, the molar enthalpy for oxygen. Okay, you could look at the molar enthalpy for anything, but this is specific to the oxygen. Okay? Let's look at another example. Find the enthalpy change when 5.5 grams of pentane burns. Okay? So this time I'm given a mass. I'm not given a reaction, I'm given a specific mass. Now pentane, what is pentane? If you've completed the organic chemistry unit already, you may know what pentane is, but if not, pentane is a common molecular compound that's written on page 4 and 5 of your data booklets. There's a bunch of common compounds. There's formulas for them with their name, I believe in alphabetical order, as well as some energy values. You don't have to worry about those for now. For now, you're going to use page 4 and 5 just to look up what pentane is. Pentane is C5H12. Okay? And notice how I'm also given, again, if you didn't say that this was just the H by itself, it would look at the units to know that kilojoules per mole means this is my molar enthalpy. In the formula that we use, that stands for the H, not the delta H, the H. Okay? And it's asking me for the enthalpy change. So it's asking me for the delta H. Again, I have, sorry, sometimes my pen does weird lines. I do have a C there again because this is another combustion reaction. So just again, showing what reaction type we have. So I have the formula delta H equals NH. And I also have the formula that N equals mass over molar mass. Okay? Sometimes I like to combine my formulas because it makes it easier to do it all in one step in my calculator so that I'm not worrying about rounding an answer too early and affecting my results. So if I rearrange this and put in mass over molar mass for my N, it's now going to be mass times molar enthalpy divided by molar mass. Now, I've mentioned this to my students before. When you're calculating the molar mass of a substance, so I've seen students do it stepwise and it takes a really long time. You want to try to be as quick and efficient in this as possible. So what I would recommend doing, open your calculator, and in your calculator put 5 for the number of carbons, and then in brackets put the molar mass of each carbon, and then add it to put 12 for the number of hydrogens and the molar mass of each hydrogen, and then hit enter. Do it all in one quick step. So 5 carbons, which are 12.01, plus 12 hydrogens, which are 1.01, gives us an answer of 72.17. Always double check your molar mass, because it would be a shame to get this whole question wrong just because your molar mass was wrong. So I'm going to input my values. I have 5.50 grams times my molar enthalpy of negative 3244.8 kilojoules per mole. So that means the mole is on the bottom. I also have a number on the bottom, 72.17 grams per mole. Now I mentioned this in another video, and you don't have to do this, but this is something that I like to do for unit analysis. Again, when I have a denominator in the denominator of an overall fraction, it moves up and becomes part of the numerator, okay? You don't have to do that. Your moles you'll still see cancel, but I like to do this to say, okay, my moles cancel, like just have 2 lines for everything. My grams cancel, and notice how I'm left with an answer in kilojoules, because kilojoules is what I have left on the top. Whatever you have left on the top is always the units of your answer, okay? So in my calculator, I'll go 5.50 times negative 3244.8, hit enter, and then hit divide by 72.17. And you should get an answer of negative 247.28, so on. Again, the units we just found were kilojoules. Now, sig digs. This time I'm not given any balancing coefficients. I'm actually given a specific measured mass. So that does affect my sig digs. While I have 5 sig digs in my molar enthalpy, there's only 3 in my mass. So that means I'm limiting my answer to 3 digits. So I don't cut off the decimal and need scientific notation. I am cutting off a 2, so it doesn't round anything up. It's negative 247 kilojoules for your final answer. Okay? See if we have another example. We do. When methane is burned, oxygen is consumed. Determine the mass of oxygen. If the change in enthalpy, so the change, and notice again how the units are kilojoules, so that right there would be our delta H. Again, this is a combustion reaction, so I can still put a little C there. And then it says the molar enthalpy for the oxygen. If you're looking for the mass of the oxygen, you need to know the molar enthalpy of the oxygen as well. It has to be the same substance. Methane here is actually completely irrelevant to this question. We don't need anything to do with methane. We're focusing on the mass of oxygen, so I need the molar enthalpy of oxygen. That in kilojoules per mole gives us our H, or our CH, for the fact that this again is a combustion reaction. So I had my formula before where I combined molar mass formula with this molar enthalpy formula. Okay, so mass over molar mass is the moles, and the H again is the molar enthalpy. If I want to rearrange and solve for my mass, I need to first get rid of the molar mass on the bottom. So I multiply molar mass on both sides. That's going to cancel the molar mass. But I also need to get rid of the H. So I divide both sides by the molar enthalpy of combustion of oxygen to get the H to cancel. Okay? Again, if you wanted to write this, pretend I have no little letters, just delta H equals NH. I can solve for N first. I can rearrange and solve for N. Once I have N, I can find mass with moles times molar mass. And again, if I were to rearrange for N, I would divide both sides by H. Okay, so you could do it in 2 steps. But if you do it in 2 steps, remember when you get an answer, you leave it completely unrounded in the next step. Okay? I'm going to do it in 1 step here though. Now, what is my molar mass of oxygen? This is very important. If you forget, oxygen is diatomic when it's in its element form or its gas form. You're going to forget that it's not just 16, it's 32. I have 2 oxygens in my oxygen gas molecule. Okay? So if you mix up that molar mass, again, it's a shame to get the whole question wrong just because you had that wrong. Don't forget your diatomic elements. If I were to quickly review them, your diatomic elements, I use the saying Haber-Finkel. Okay, that's hydrogen, oxygen, bromine, fluorine, iodine, nitrogen, chlorine. Those are my diatomic elements. And then don't forget, if you had phosphorus in its elemental form, it's P4, and sulfur in its elemental form is S8. Okay, so just a little quick reminder there. So I'm going to take my molar mass, which was 32 grams per mole. I'm going to multiply it by the enthalpy change, the delta H, which is negative 250 kilojoules. And then I'm going to divide it by the negative 401.3 kilojoules per mole. And again, I'm going to move that mole to the top. Okay? So looking for my unit analysis, my kilojoules cancel because they're on the top and the bottom, and my moles cancel because they're on the top and the bottom. So I am left with grams on the top, which indicates that yes, we've rearranged this formula correctly. So now if I do my calculation, I'm going to take 32.00, multiply it by negative 250, get my answer, and then divide my answer by negative 401.3. And you should get an answer, if you try that on your own, of 19.93 so on grams. And again, going back up to the question, there's 4 sig digs in my molar enthalpy, but only 3 in my enthalpy change, my delta H. So that limits me to having 3 sig digs. So that's going to lead me to round it to 19.9 grams as our final answer, right? We're cutting off a 3. The 3 doesn't round anything up, right? I always look at the digit I'm cutting off and the last digit I'm keeping. If the digit I'm cutting off was 5 or more, it would round the 9 up, which would actually bump this 9 up and make it 20.0. But I'm cutting off a 3, something less than 5, so it does not round up. Okay? And I believe that is it for this lesson. Thank you very much for watching.